So what we're going to do today is to finish the algorithm, how to solve almost route problem on expanders. Okay, let's recall the goal. The goal is that you get a graph, you get a demand, and some slack parameter epsilon. You either return a cut, we call it a violating cut, which just says that this demand is not routable with condition 1. Just certify that this is not possible because the total demand is just too big compared to the size of the cut. So we either find this cut or you return a flow, which basically route most of the demand in the sense that the residual demand can be routed with really small congestion. Okay. And the key idea was what? The key idea is that like our strategy is to either find a cut or a flow. Okay. And we want to find the flow such that the residual demand is like respect this thing. Respect this one. Yeah. Okay. And okay. So Michael make just talk to me now that there's something to clarify. So we said that for any what is so this thing is the demand, which is like vertex demand, but when we talk about expanders, we kind of say before that given a pair, a set of pairs of demand, as long as it respects the degree, then you can route with low congestion. But the notion of demand, the pairs of things and this vertex demand are a little bit different, right? So let me clarify this. So we said that okay, phi expander is such that for any demand which is vertex pair, okay, and that respect degree, respecting degree is routable with congestion 1/5. Okay. And so now we kind of say that I want to claim that this thing just implies that for any vertex demand that we just talked about, for any vertex demand, these things look like these things looks like you have UV and you say that you want to send 2 here and maybe a XY and you want to send 3 here. But vertex demand here looks like you have +1, -2, and +1, maybe something like this. Okay. If this is true, it means that that respecting degree is routable with congestion 1/5 too. So why is that? Maybe I make it +2 plus, maybe make it like this. Yeah. Because given this demand, you can define a pair of demands such that you can define this kind of demand, for example. If you want to route it this way, you can route it. If you want to route it even in this way, you can route it too. So this sometimes is called single commodity demand. And this thing is called multi commodity demand. So this thing is kind of basically stronger, right? You can control how you want to pair up, how you want to route from source to sink. And this one, you just kind of say that, okay, there's something from the source, you want to route to sink somehow.
Is there like an intermediate thing where like you have certain subsets of nodes where within those subsets you have like sources in sync but don't care about within each subset it's like a single commodity flow? Or is that like equivalent to something else?
So this thing is strictly weaker than this one, but for your version, it's basically as strong as this already. Because once you have like a spiral subset, like the subset itself can be just one node too.
Oh, okay.
So like each subset pair can be one node. So it already modeled this one.
Okay.
Yeah. Okay. Questions? Yeah.
So just to clarify, like for the single commodity demand, like if it's A-respecting, is it going to be a bit different than the multi-commodity one? Is it just going to be like the demand of this node is less than the node weighting of this node, or?
Oh, this thing really just means that like dV at most degree V for all V. Okay. Yeah, for all V. Yeah, with absolute value because this thing has negative. Yeah. So it captured the same intuition. What we want to say is just this thing is more expressive. Yeah. But today we just talk about single commodity flow problem. So yeah. Okay. So that's our strategy, right? And what's the algorithm? Let's record it. We just first like check if there is some trivial cut that that we can just return just by looking at the demand on each node and see if it's more than degree. If so, then you can just if this is more than this, then you can just return the cut. So otherwise, we just like make a first check here. And then what we do then is like start the weights on each node, like plus weight and minus weight. Initialize them with 1, then define the potential. Again, the potential will basically, we discussed the intuition last time. The potential on each node basically correspond to the excess up to now. Okay? If the excess up to now, on average up to now, is positive, it have excess, the potential will be like exponentially positive. If it has deficit, it will exponentially like become negative. That's the potential. And then on each route, just look on each edge. Send flow at full capacity from higher to lower potential node. Super like greedy, okay? And then what we check next is just check this thing. Kind of basically, it's kind of, yeah, it's check this thing. It's kind of check like when you sort vertices into line, are there like a lot of excess and a lot of deficit on the opposite side, basically. This is kind of what it measures, right? You kind of see this, right? Like this thing is just kind of, yeah, I draw it. You put vertices into line according to the potential. This is like a 0. And if there are like, if this is like a positive side, if this is negative side, if there are a lot of node with excess and a lot of node with deficit, then this inner product will be big. Hopefully you see this. Okay. If it's big, then you get to this case, and we're gonna see how to get a cut. If it's small, then we update the weight. Okay. How? Like you see, like we just update the weight according to like the excess. Okay. If the excess is big, the weight plus will increase. If the deficit is big, then this thing will increase a lot. Okay. Anyway, we proved last time that if, like in each round, you always get this inner product to be less than 0, then you get the flow that you want. You get a flow such that the residual demand, the excess is small. The excess can be routed with low congestion. So today we're gonna just continue and see that if we get to this case, we can find a cut, a violating cut. Okay. Okay. So, okay, so we get to the case when this is not just F. Yeah. When this inner product between the potential and X and excess vector is more than 0. Okay? And we want to find a violating cut. When this is the case, it really just means that this inner product between potential and the flow out vector is smaller than inner product between potential and demand. Okay. And we just analyze this thing, and we see that it's just exactly this sum. Summing over all edges, and you multiply the weight, the capacity of this edge with the difference of potential. So each of these terms is always positive. Okay. And why this is the case? This is exact, like we get this equality exactly by like how we construct the flow on each round. Okay. Like this basically the reason why we construct the flow in such a greedy way. Okay. That's why we get this. Okay. Okay, now, so what we get is like this thing is basically smaller than this one. Okay. And what I'm going to do now is just to say that, okay, actually, if I have any potential at all, and if it's such that this sum for this potential is less than this inner product, then I can find some cut, some violating cut. Okay, so let's see how. Okay, so first I'm just gonna sort vertices according to the potential. Okay, so the potential is this, and I sort vertices. This is V1, V2, up to Vn. Okay, this is potential. V1 is less than potential of V2, and so on. Vn. Okay, and what we're gonna do next is just that. I said that I can actually assume that like V1 is 0. Okay. I want to say that actually I can assume that potential at V1 here is 0. This is 0. Why is that? Because you see that this term is the same. It doesn't change at all when we translate everything by some constant, right? Like this thing just measure the difference between potential of node U and V. So if I shift everything by something, it doesn't change. So this, if I shift every node by potential of V1, this doesn't change. I claim that. So is this clear? Now this is the case too. If I shift everything here, it doesn't change. Why? Because let's look at this thing. Yeah. When I shift every potential by like phi of V1, right? This thing is basically changed to this thing, right? Because, yeah, like, I mean, like you get phi and shift by all one vector times phi V1 multiplied by D, right? And this is just phi inner product with D minus like phi V1 D inner product with D. But what is this? This is 0. Right? This thing is just a sum, the total demand over all nodes. That's 0. So this term is 0. It doesn't change. Okay. So if I shift everything, then the both term doesn't change. So I just gonna shift to simplify things a bit, so that this is 0. Okay. That's my first step. And I try to make this thing to be 1 too. Okay. I just try to simplify things so that this is 0, this is 1. And how exactly? Maybe I just scale everything down so that it's 1. But maybe let me just like work with like scale everything down, like set phi prime to be phi scaled down by phi Vn. So this is now like phi prime, and this is actually 1. Okay. So let's work with this thing. Okay. One sec. Okay. So now consider this. Okay, so what I'm going to do next is this. Maybe let me tell you the strategy. Okay. What I'm going to do next is I'm going to consider like a random threshold tau between 0 and 1. Some random threshold tau here. This is random threshold, but this random thing is just for analysis. In our algorithm, there's nothing randomized. This is just for analysis. Okay. And what will happen is that then I just consider S tau to be like the cut containing everything up to tau. So S tau is just everything, all the nodes, such that, yeah, it's at least tau. This is S tau. Okay. And it's going to be the case that I can relate my expected cut size by this thing and my expected demand inside S tau by this product demand. We will prove this soon. But suppose that's the case, then what do we know? We know that this one is smaller than this one. Right? Because phi here, like when this is phi, this is like this term is smaller, but phi prime is just scaling of phi. So this term is smaller than this one. Okay. So if that's the case, then it means that this term is smaller than this term. Are we good? If this is smaller than this, then what does it mean? It means that the excess tau, such that the cut, if you get these two things, then you get that this thing is less than this. then it just means that there must exist some tau, like without expectation. There exists just some tau, such that the thing inside here is smaller than the thing inside here. Because otherwise, if there is no such tau such that this thing is smaller than this, then in expectation this cannot be smaller than this. Okay, that's our strategy. So let's now prove it. Is the strategy clear? Okay, let's prove it. So what we're gonna do here is like let's understand the expected cut size here. Okay. So the expected cut size is just gonna be really like a sum over all edge, the capacity of the cut of that edge, and the probability that this edge is cut is in like the cut of S tau. Right? What is this probability? An edge is cut. Basically, if the two endpoints of this edge, like one is here and one is inside S tau. Okay. So this can be, if this is, what is the probability that this thing, like when you have U and V, what's the probability that tau lie between U and V? That's when it's cut. Yeah.
Would it just be the distance between the potentials over the whole disk, which is just one?
Yeah, exactly. So this probability is then just the distance between this thing over the total distance, which is just one here. So that's why we get like this probability is just this distance. Yeah. Okay, so that's our like expected cut size. And now what's this? Expected total demand. Again, this is summing over all nodes, right? And we like the demand on this node and the probability that V is in S tau. Okay. What is the probability that V is in S tau? Like maybe V here, V prime is in S tau. Well, this happens when tau is like, this happens when tau is like less than the position of V. So this is just the probability that tau is less than position of V. And that's just really just position of V, like, because it's basically, you see this, I guess, So, and this is just like inner product between phi prime and D. Okay. So that's it. So now it just means what? It means that there must exist some tau such that the cut size actually is less than the total demand inside. Okay. And once you know this, you can find it fast. Yeah.
So where did this like translation and scaling come in? Because it seems to me like this entire argument is pretty much independent of where the potentials are actually lying.
Yeah, good point. So I really just translate and scale just so that the calculation looks a bit cleaner.
Okay.
Otherwise, when you calculate like the right, you see that this probability.
Okay, that lets us choose the tau in the unit interval as opposed to dealing with something.
Yeah. Like if otherwise I need to choose tau to be like the minimum potential, the range is minimum potential to the maximum potential. Mm-hmm. And everything will just work actually. It's just the calculation looks a bit more things to calculate. That's all. Yeah. So nothing really is happening to translate and to scale. Yeah. Good. Okay. So back to this, like we now know that there is some threshold cut. That is a violating cut. How to find it fast? How would you find it like fast? If I promise you that there is a cut of this form, how to find linear time?
I mean, there are only linearly many threshold cuts.
There are only linearly many, yeah?
I'm not sure how expensive it is to check each one, but it doesn't seem
Right.
like that should be.
If for each of this guy, you can really literally just check it in linear time.
Yeah,
But there are still linear many cuts.
Yeah. Oh, we can just binary search it then, right?
Binary search, not clear. Like yeah.
Well, I guess could we would like make tau like the potential, then like check all of the positions, but that would still. I mean, is linear fast enough for this, or?
We want to spend the total time linear.
Okay.
Yeah.
We did something similar to this the other day, right? Like you sort of, I don't know, you like
Sweep.
go through, yeah, you sweep cut, right? You like keep track of like all of the edges that are to the right of like the pointer and to the left of have like one endpoint to the right and one to the left, and you like sort of
Exactly.
go, right? And so you only like look at each edge. You
Once.
need to add it and delete it once.
Exactly. Like what I do first, I know that the cut looks like a threshold cut. So what I need to do first is just to sort vertices. Okay, sort it in n log n time. So first sort it and then put it into like order. And now like just sweep. Like look at this one, which is like you now compute the cut size of this one, and then you can look at the cut size of the next one by just spending time proportion to the degree of the next guy. The next one, you just spend time proportion to the degree of this guy, and so on. So you really can like compute all this cut size in time, the sum of the total degree. That's linear in M. Okay. So that's it. Yeah, like you see how to do it now. Yeah. So whenever this thing happen, you can get a cut, violating cut in linear time. Okay. Like linear, like M to sweep, but n log n to sort. Yeah. Okay. All right. So that's basically it for expanders. We now basically can solve almost route on expanders. And you saw that if we can solve almost route, you can solve route. You can solve approximate Maxwell just by kind of repeating almost route log n times. Okay. Now let's do it in general graph. Okay. And the key idea is to use tree-flow specifier to generalize the algorithm from expander to general graph. You might wonder, like, tree-flow specifier is a crude approximation object, right? It's like something that approximate you, like, give you like polylog approximation. How come it's useful for like 1 plus epsilon approximation? So let's see. We're gonna see it now. Okay. So I claim that this is a problem. My claim is that if I give you tree-flow specifier T of G with quantity Q, then we can solve almost route in time M times Q squared times log over epsilon square. So the quality here just affect your running time. It doesn't affect your approximation. And this actually will happen quite a lot in like a fast algorithm. Like you come up with like crude approximation objects, and then you try to find a way to boost it to like a accurate approximation. But the crude approximation just affect the running time. This happens quite a lot. Okay, so so you see this, and then after class you try to prove the same thing, that even if I gave you 3-cut specifier, you can prove the same thing. Yeah. And because we see, but in class we see how to build 3-flow specifier with this quality in this time. So now it means that you can solve almost route in almost linear time. In literature, we actually know how to build this with like polylog quality and nonlinear time, and that actually would imply improvement to this to just like instead of interleader one, you get only polylog. Anyway, we didn't see this one, but we saw this one. Okay, so what's the key idea? The key idea is this. Suppose that I have 3-flow specifier. Then when I have a 3-flow specifier, yeah, maybe like this. Okay. This is my tree, and vertices of the graph is here, right? This is V. Okay. Then, like, this tree defines some laminar family of the set of vertices in a supernatural way. Like, basically, this guy just corresponds to this set. This guy corresponds to this set. This guy corresponds to this set, and this guy corresponds to this set, and this one corresponds to the whole thing. Okay. So let U be the laminar family of vertices of vertex sets defined by T. Okay. And now here's the thing that we actually know. Suppose that there's some demand. Okay. Imagine that I have the demand D. Okay. Maybe like demand D plus 1 here, minus 1 here, plus 2, minus 1, maybe. Yeah. Then if I want to route this demand on this tree, okay, then I will have some congestion on this tree. But suppose that it's a case that, and recall one thing, you all recall this because I think I asked all of you in this exam, the capacity of this edge is just, if this is a set U, the capacity here is just the cut size of U, right? So suppose that when I try to route this demand, what if the congestion to route D is at most epsilon over Q? This is the same thing as saying that the total demand inside the set is at most this thing, right? Like the total demand here inside the set, for example, this one, the total demand is less than this thing by epsilon over q. This statement is the same thing as saying that the total demand is less than the cut size times epsilon over q. Okay. Suppose this is the case. The congestion to route D is at most in T. Then we all know that if this is the case, if the congestion to route in T is at most epsilon over Q, then the congestion to route D in G
It's epsilon.
is at most epsilon. Right? Because this T is the three flux specifier with quality Q. So you blow up the congestion by Q. Okay. So then get that D is variable in G with congestion 1 over epsilon. Okay. So this is basically our strategy. We want to find a flow such that the residual demand, like we want to find D such that the DF residual demand is routable in T with congestion epsilon over Q. If that's the case, we are done. What does it mean to have small congestion in T? It's just the same as checking this condition. This condition. Are we good? Okay. So if df is small for every cut here, then df is routable in T with this congestion. So df is routable in G with this congestion. Okay. So now the goal is just to find f such that this is true. Okay. So let's compare it with what we did before for expanders. What we did for expander is that for every node, we want to find a flow such that for every node, the total demand on each node, the excess on every node, is small compared to the degree. So there are like basically n things that we need to check for every node. Now we check this for every cut in this family. How many cuts are there?
N log n?
Actually, just even at most 2n, yeah. The tree, yeah, at most 2n, like basically around n, yeah. There's just 2n many cuts that we need to check this. Okay. So like the task doesn't get much more harder at all.
Sorry, a moment ago you said that for each node you had to like check its degree or something. And
yeah.
That would. I see. Wait, but that would only take time n, or would that take?
Previously we checked this thing, like kind of we want this thing, degree v for all v.
Right.
But now we want this.
Okay. Yeah. Okay. Gotcha.
Okay. So I want to contrast this with like a trivial thing a bit. Basically, when to say that like this thing is routable with congestion epsilon, that statement is just is the same thing as saying that this is at most epsilon, the cut size, for all subsets. This is the same thing as a routable with congestion epsilon. So compare this thing with this. This has 2 to the n many cuts. If you just take it from the definition, what it means to be a routable with congestion epsilon, you need to check 2 to the n many cuts. But with 3-flow specifier, now it allows you to just check 2n cuts. Super strong. You just need to make it a bit smaller than like epsilon. Like now it's epsilon over q. But you reduce the problem from exponentially many cuts to linear using the 3-flow specifier. Like super amazing. Okay, so now let's do it. Okay. So the problem is just here. The algorithm now is just here. Almost the same. You have this family U from the 3-flow specifier. Then the first step, you just make like a trivial, like a check, sanity check that for every cut in your family, right? The cut size is bigger than the total demand inside it. Okay? Because otherwise, just return U. You can just return this as a violating cut otherwise. And now I initialize the weight. The weight now is just not just defined on every node, but for every set in the family. I have WU, like the weight for U plus, W weight for U minus, like before, but define it for every set in the family. And then I compute the potential. Okay. The potential used to be just like this thing over this thing, degree of U. But now actually it should be here. Now I change it a bit, like because I change it to be like sum over all the set that contains U. And this is just almost like before, but it's for capital U. And I replace the degree of U by the cut size of U. Okay. So that's how we define the potential. Still, like just put every vertices into a real line. That's the potential. And once you have the potential, you define the flow like before. Just send from higher to lower potential. And now, if this is small, then what we do is to update the weights. Now there are weights for every cut U, for every set U. So what we do is just to compute the relative excess at U. It should be like the total excess at U over the cut size of U. Okay. Not the degree, but the cut size. And that makes sense because like this basically kind of measure how much congestion U will cause on the cut around U. Okay. And then you update the weights according to the relative excess like before. Then you go to the next round. If this is less than 0, this is more than 0, then you get a sweep cut. Like you do a sweep cut and you get a violating cut. This step is just the same, nothing new. Okay. Is the algorithm clear? Okay. So once you are done, after all the rounds, you just return the flow, which is the average flow, like before. Okay. And the running time, I let you think about it, but nothing is complicated actually. Like basically the total running time per round is still linear in M. And so what's the total running time? Actually, I didn't say this, but T, I should highlight this in red. Alpha here is like epsilon over Q. Okay, so the running time is gonna be this thing as we claim. Now about why, so there's nothing else to prove except that now we said that the running time is fast, and if it return a cut, it's just the same proof. It's literally just the same thing because it's the same situation. The only thing left is just to say that, okay, if it return a flow, then we get this. We get that this residual demand can be routed in T with low congestion. Okay. So, but it's gonna be the same. Basically, everything, I literally just copy the same proof and replace the node set. Previously we do it for every node in U. Now we do it for every set U in the every capital U with a family U. You do this, and we replace the degree of U by the cut size of capital U. Okay. And then everything works. So let's go through it very quickly before we finish. Okay. So how did we do this? We basically apply multiplicative weight update, which define the gain vector per round. And this gain vector should have bounded width, the infinity norm of the gain vector should be small. And also, if the gain vector is such that the inner product with our weight is small, then at the end, the average of the gain vector is small on every coordinate. That's what happened. Okay, so let's see quickly. We just define the gain vector. We set J, the set of indices, to be U times plus and minus. And the gain for U plus is just the relative excess at U. The gain for U minus is relative excess at U, negative of that. And you can go through the same thing, which shows that relative excess have absolute value at most 2. So this is at most 2. And that's just because I don't know if I should go through it, but it's just the same proof. Yeah, the total, we have that if you look at the excess at U, which is the total demand at U minus the flow out of U, I'm gonna bound the absolute value of both terms. This is at most the cut size of U because we checked this in the first step. This one is more the cut size of U because we flow out of U by at most the capacity of each edge. So the flow out of U is at most the capacity of all edges crossing U. So you get this. So now it means that this thing is almost twice of degree. Sorry. Yeah. Cut size of U. So this is almost 2. And you can see that the way that we update the weights is just exactly the same as multiplicative weight update algorithm. So we just update it according to multiply it by exponential of the gain. Okay, So we do it like before, like how we should do here. This is just to update the weight by multiplying by exponential of the gain. Here too. And then this thing, you can verify that it's the same thing here. I will not go through it. Okay. And then, now the point is that by the end, then you get that for every cut U, the total excess at U is at most the cut size multiplied by this one. Because we set alpha to be epsilon over Q. So it contains some calculation. Maybe you just need to see the calculation. But the point is that it's just really the same proof. Just change the object from the set of singleton in like the set of all nodes in expander. Now we change the set of singletons to the set defined by tree-flow specifier. The point before was that the relative access on every node for expander, at the end, the access on every node will be small. That is the access respect the degree. Now what we do is just for every set on the tree, on the tree here, the total access on every set, not just on singleton, every set access, the total access on the set is small compared to the cut size of that set. So we just try to get this basically. And we get that.